Okay, so good evening, everybody. This is Nitish from Dr. Gunjan's lab at IIT Hyderabad, and I'm going to today we are discussing a few questions from week two. Okay, so let's start from the slide one, and the first question is that for a voltaic cell, which of the following is most true? Okay, one reagent must oxidize, one reagent must reduce, the two reagents must not be in contact, and all of that. Now, people see the concept of this is that there are two electrode. One is it's not like the copper is negative or zinc is sulfate, but they are based on their comparative charges. One is your positive electrode and one is your negative electrode, as we all know. Okay, there is a salt bridge that basically connects between these two. Now, what happen at cathode? Okay, oxidation occur, but at cathode loses the electrons. Okay, that moves towards the anode, and at anode basically the free electron that get uh, uh, reduced, okay, in presence of zinc. So here what happened at one voltaic cell, this is the entire voltaic cell. In half cell oxidation occur, half cell reduction occur. So one reagent must get oxidized, one reagent must get reduced. So the answer will be your all of that. Now, following are the delta G for some reactions. Which of these represents a spontaneous reaction? Now, if you see the two graph, in the first one, the reaction, the del G is less than 0. Okay, and the second one is del G is greater than 0. So if you'll see at this, when del G is more than the 0, it requires more time. Okay, it requires more time to complete the reaction. Okay, because and even we need additional energy to it, because the reaction is not spontaneous, because they need the free energy is very high, gives free energy. Okay, so when del G is less than 0, that is del G is negative, then the reaction is supposed to be spontaneous, and if a reaction is spontaneous, it will occur automatically. We don't need to add additional energy. So if you'll see this here, the value that is minus 100, 0, 100 and not the above. So the value that is in minus, that is minus 100 kilojoule, del G always negative for spontaneous reaction. Okay, so whenever it is a spontaneous reaction, but del G will always be negative. Okay, now salt concentration in salt breeze is less than the half cell. Salt breeze क्या होता है? So salt breeze is a device used to in an electrochemical cells for connecting its oxidation and reduction half cell, as we have seen here. If you can see here, if in the left side is your oxidation half cell and the right side is your reduction half cell, both are connected by salt bridge. So salt bridge is a part, and it is a very important part to maintain the balance between the ions, right? So reduction half cell wherein weak electrolyte is used. So here we basically use a weak electrolyte. Now why weak electrolyte not strong? Because strong electrolyte directly reacts, but weak electrolyte used in balancing the acidity or basicity between the two halves. In other words, a salt bridge is a junction that connects the anidoid and cathodic compartments in a cell of electrolytic solutions. Okay, so basically salt bridge is there to balance, and it is there to maintain the two half cell. Okay, so basically the salt concentration in salt bridge is more than the half cell. Okay, so that it can balance. Now select the correct notion for a cell. So double vertical line for salt bridge and single vertical line is for your uh, phase boundary between solid metals and its salt solution. Okay, so a double represents your salt bridge. So first denotes your phase boundary. So the option will be 2. Okay. Now this is what ideal concept of stranded hydrogen electrode. Okay, just so we are here at the strong hydrogen electrode. So the standard hydrogen electrode, that is SHE, is assigned an electric potential that is zero. E0 is equal to 0 volt, which used as a reference to measure the electrode potential of other half cells. Now we need some standard. So basically, standard hydrogen electrode is a standard with zero potential. So based on which we calculate the potential of the half cells. So what is the construct of this particular thing is that there is a platinum wire or it is a platinum electrode present at the and we the hydrogen gas is basically used at a pressure of 100 kilopascal at 298 Kelvin and 1 mole dmq, that is the concentration. Okay, so 1 mole per dmq volume at with standard hydrogen electrode, standard platinum electrode with 1000 kilopascal of pressure and 298 Kelvin temperature is basically construct your standard hydrogen electrode. So which of the following is not true about the SHE as we have discussed previously? So it uses a platinum electrode. Yeah, it uses. Now hydrogen is bubbled at a pressure of 1 mmHg. Is it 1 mmHg? Yeah, tell me. Yes. So basically, the standard hydrogen electrode is not 1 mmHg. You can see here there it is 100 kilopascal, right? So H plus ion is equal to 1. That is true. So the answer will be hydrogen is bubbled at pressure of 1 mmHg. Now for a balanced reaction of SSE with 1 mole of hydrogen gas, how many moles of electrons are released, right? So 4 mole of electrons are required to produce 2 moles of hydrogen. So and 2 moles of electrons for every 1 mole of hydrogen gas. So it will be 2, because for every mole it needs 2 moles of electron for 1 mole of hydrogen gas. And for 4 mole of electrons are required for 2 mole of hydrogen gas. Okay. In SHE, there is standard hydrogen electrode. Now, which of the following is better oxidizing agent than others? So, if you see this table, oxidizing agent is basically which of the following is the best oxidizing agent. Now, what are the conditions? What can be the best oxidizing agent, right? Now, if you see here in the top, that is fluorine is there, so it can loses electron easily. Why? Because you can see the electronic configuration 1s2, 2s2, 2p5. Now, if it loses 2, then it will be half filled, complete half filled, and it can be into this stable condition that again further cannot withdrawn electrons. Right? That is a very strong conditions because it is 1s, 2s, and 2p. Okay, so F2 is a good oxidizing agent that metals, quartz, and if you see other things like lithium, that is in the bottom, and if you see the electronic configuration of everyone, so you'll find fluorine is one of the most suitable oxidizing agent that then lithium, potassium, and silver. Now the net driving force for a reaction is given by Nernst equation, because it is one of the most important equation in electrochemistry to calculate the cell potential. We can calculate the standard state condition like E naught based on the equation, that is E is equal to E naught minus 2.30 TRT by NF log 10 Q, where E is your potential in volt, E0 is the standard potential in volt, R is the gas constant, T is the temperature in Kelvin, N is the number of moles of electron transferred, and R is your Faraday constant, and Q is the reaction quotient. So at standard temperature, that is 25 degrees Celsius and 298 Kelvin, if you put the RT value, that is R is equal to 0.634 into 10 to the minus 7 joule, and T is your 298 Kelvin. 298 Kelvin. So the equation is basically E is equal to E naught minus 0.0592 by N log Q. So this is a very important formula that generally people you need to recall, and so that you can use in further. Right now, Q is your basically product reaction quotient has usual form like product by reactant, product to the power X and reactant to the power S. So X and Y are basically the product quotient. That is basically the number before that, like uh, 2H2, 3H2, like that. Okay. So the table of standard reduction potential gives the voltage at standard condition, 1 molar of for all solution, and one calculation of cell potential, yet other condition of the concentration and pressure. Now again, this is the another form of Nernst equation. E cell is equal to E naught minus RT by NF ln Q, and there is 2.303 RT because ln is equal to 2.303 log E का value. ठीक है? So the non equation enables the determination of cell potential under standard condition. It relates the measured potential to the reaction quotient and allows the accurate determination of equilibrium constant. So we can calculate the equilibrium constant. Okay. Now for SHE at 25 degrees Celsius, the absolute electrode potential is basically 4.44 plus minus 0.2 volt at 25 degrees. So, but from a basis of comparison with other electrical reaction, the SSE voltage is considered to be 0 volt. It's not like it's absolutely zero. It has a voltage that is 4.44 in plus minus 0.02 volt. But in order to compare, like we want to compare different half cells, different battery, different like that, okay, right? Other reactions. So we take this as a control. We take this as a standard. That's why it is called standard hydrogen electrode, and it is considered to have 0 volt. Now, which of the following is not true to choose an electrode? So basically, an electrode should have the ability to catalyze cation reduction reaction. It should reduce, it should oxidize, it should allow in reproducing the potential generated. Definitely, it should be able to, if potential difference is not there, then the reaction will not occur. It should have a high intrinsic exchange current density for reducing protons. That is also required because if uh, the मतलब proton density changes नहीं होंगे, then uh, it will not smoothly conduct the oxidation or reduction part, and in that case the smooth connection and supply of electrons will not be there. So basically it should be extremely reactive. So this option is not required, it doesn't need to be reactive at all. Rather, it need to have some ability to oxidize, reduce, and maintain a potential difference, and that is what required to transfer electrons, and the transfer of electron is basically the transfer of current in the opposite direction. So okay, so the reaction is need not to be reactive. Okay, so that's it from today's class. Thank you so much guys for your attendance, and we'll see you on the next class. Thank you.